Today we're looking at a beginner Java programming problem called Unique Characters in String, courtesy of firecode.io. We'll define the problem and look at some example inputs and outputs, design and implement two solutions to the problem in Java, and finally analyze both algorithms for both their space and time complexities. Let's get started. So for our problem, unique characters in an ASCII string, we need to write a method that returns true if the input string has all unique characters, and false if there's even a single repeated character. So if all the characters in the string are unique, we return true. If there's at least one repeated character, we return false. So some examples: if we receive A, B, C, D, E as our input string, we'll return true because there are no repeated characters. MADAM, we will return false because there's at least one repeated character. They're not all unique. In this case, we have two repeated characters, both the M and the A. Finally, if we receive the empty string as input, we will return true because there are no repeated characters. Let's go to the whiteboard and sketch out a solution. So suppose this is our input string. Our first algorithm is going to use two loops. One loop will start at the first character. The second loop will scan the rest of the string looking for that character. So we'll start on the G and scan the rest of the string looking for the letter G. If we find it, we can return false immediately because the characters are not unique. If we don't find it, we'll advance to the next character and again scan the rest of the string for that character. So our first loop will go from character index 0, the first character in the string, all the way to character index n-2, where n is the length of the string. Character index n-2 is the second to last character in the string. The inner loop will go from 1 greater than the current index of the outer loop, so I plus 1, and it will go until the last character in the string, which is index n-1. If at any time we find a duplicate by comparing the character at index I, if at any time that equals character at index j, we can return false because the characters are not unique. We found a duplicate. If we make it all the way through the two loops and we don't find any duplicates, then at the end we can just return true. Let's go implement this in Java. So for the implementation, our first loop will go from the first character in the string at index 0 all the way till the second last character in the string. Our inner loop will start at the character immediately to the right of the character indexed by the first loop and go to the end of the string. And we simply compare the characters at both of those indices. And if they're the same, we can return false. If we manage to get through both loops and we don't find any repeated characters, we can return true at the end. Let's submit our code and see if it passes all the tests. Great, so it passes all the tests. Let's do an analysis now. So we'll start our analysis by doing an analysis on the time complexity of the algorithm, and we'll do that relative to the length of the input string, and we'll say the length of the input string is n characters. So if we look at the operations in the first two for loops, we see we instantiate a couple of integers here. We do some integer arithmetic. We do some integer subtraction, integer increment operations here. All of these things are constant time operations in Java. That is, they don't rely or depend on the size of the input string. They're all constant time operations. Same with the string length operation here and here. That string length is a constant time operation in Java. the length of the string is stored as a property of the string class. So when you ask the string for its length, the length doesn't need to be calculated. Finally, inside the inner loop here, we do some char@, method calls on the string class. So in Java, you can access any character of a string at any index in constant time. And that is time not dependent on the length of the string. So every kind of individual operation within our algorithm is a constant time operation. So the next question is, how many times do we have to do these constant time operations in the worst case? And the worst case for our algorithm will be when the input string is of all unique characters. So for example, if the input string is A, B, C, D, E, it's going to go through both loops and the inner loop several times, comparing characters before eventually reaching our return true statement at the bottom here. So if we had, for example, input string of A, B, C, D, E, let's count how many times we'd have to perform this comparison on line 15 here. The first time through, I is equal to 0, and we would do 4 comparisons, comparing A with B, C, D, and E. So we would compare it, do 4 comparisons of line 15. The next time through, I would be 1, so we'd be looking for B, and we compare B with C, D, E. So there'd be 3 comparisons. So line 15 would execute 3 times. Next time through, I will be 2, and so we'll be comparing C with D and E. So that will be 2 executions of line 15. And finally, we'll be comparing D and E, so line 15 will execute once when I is 0, 1, 2, 3. So in total here, for our string of length 5 in this case, we will be doing 7, 8, 9, 10 executions of line 15 here. So generalizing then, if we have a string of input length n, we will be doing n minus 1 plus n minus 2 plus n minus 3 all the way down to 1 comparisons on line 15 here. So line 15 will be executed this many times. And if we add up 1 plus 2 plus 3 all the way up to n minus 1, that equals n minus 1 times n divided by 2, if we were to add all those up. Just like if we were to add up 1, 2, 3, and 4, that would equal 4 times 5 divided by 2, which is 10. So in this case, this is how many times for a string of length n, line 15 will be executed. Multiplying that out, we get n squared minus n divided by 2. And further simplifying that, it's 1/2 n squared minus n over 2. Now that is on the order of big O of n squared, which means it's an n squared algorithm. It's not a linear time algorithm. In terms of the space complexity of the algorithm, it's actually very good. We instantiate an integer here, we instantiate an integer here, which will get thrown away for every loop of the outer loop. Other than that, we'll do a couple of integer comparisons here, which will instantiate character variables, but they will be thrown away once the loop is finished. So the space complexity of our algorithm is actually constant because we have a fixed number of variables that are allocated at any one time, and it does not depend on the length of the input string as to how much space our algorithm uses. So our last algorithm was order n squared, and we want to improve on that. What can we do? Well, instead of scanning through the string multiple times, like we did with the first algorithm, we'll only scan through it once. So we'll have one loop going from the first character all the way to the last character. Remember, the length of the string is n. And as we scan through each character, we will refer to a set that we'll use, and this will be the set of all the characters that we've seen before. So our algorithm will look at the first character and check our seen before set to see if it's in there or not. If it is in there, it means we have a duplicate and we return false. If the character is not in our set, we'll just add it to our set and then move on to the next character. Again, we'll check, is this character in the set of characters we've seen before? If it is in that set, we return false. If it's not in the set, we haven't seen it before, we will add it to our set and move on to the next character. Continuing in this fashion, we'll only have to go through the string once. So up to n checks to see if we've seen the character before determining whether all the characters in the string are unique or not. And luckily for us, Java provides a hash set that is very efficient in the operations of inserting into the set and checking if an element is or is not in the set. So let's implement this in Java now and then do our analysis on the algorithm. So for the implementation of our second algorithm, we create our hash set here of characters, which keeps track of all the characters we've seen. We then loop through the length of the string, one character at a time, and check to see if the character we're currently at has been seen before. If it has been seen before, we can return false, meaning we found a duplicate. Otherwise, we add the character to the set of characters that we've seen and continue on the next iteration of the loop, looking at the next character. We continue in this fashion until either we find a duplicate or we've gone and checked every character in the string and haven't found a duplicate, at which point we return true. So let's submit our algorithm, make sure it passes all the tests. Great, so it passed all the tests. Let's do a quick analysis before we wrap things up. So analyzing the time complexity of our algorithm now. Remember, this is all relative to the length of our string, which is n. We instantiate a hash set, constant time operation. As before, the instantiation of an integer increment, and checking the length of the string are all constant time operations. Next up, we get the character at a certain index, which is a constant time operation. We then need to check whether the character is in our set of characters we've seen before. And the operation, the contains operation in a Java hash set is a constant time operation. It's not dependent at all on the length of the string. Similarly, adding an element to a hash set is also a constant time operation in Java. So we have only constant time operations here. How many times would we loop through in the worst case? Well, again, our worst case is when all the characters in the string are unique. So for example, A, B, C, D, E. In that case, we'll simply loop through from 0 to the length of the string. So 5 times, performing constant operations each time. So time complexity-wise, it's a linear time algorithm. For the space complexity analysis, a bit different than last time, in that now we have a hash set that is keeping track of all the characters we've seen. And in the worst case, as we loop through checking and then adding characters to that set's going to grow as we add characters to it. So in the worst case, we'll have one character added to the set for every character in the string. So on the input of A, B, C, D, E, our set at the end, when we were returning true here, our set would have A, B, C, D, E in it. the amount of space that we're using here is directly proportional to how many characters there are in the string. So our space complexity here is linear. So today we implemented two algorithms to solve the unique characters in string problem. The first was a order n squared time complexity but constant space algorithm. The second was linear in both time and space complexities. Thanks again to firecode.io for the use of their platform. We'll see you next time.